Hello everyone, and thank you for joining today's webinar on modeling of linear electric machines. I am Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all of the questions at the end of the presentation. Here is today's agenda. First, we'll go through an overview of linear electric machines. Then we will look into its design challenges, and then we'll use our EMWorks solutions simulate a 12 slots 8 pole single-sided flat linear electric motor and 6 slots 4 poles tubular linear electric generator designs. Later, I'll demonstrate one of our model using EMWorks 2D software, and then I'll conclude today's webinar. The motor is used to convert the electrical energy into rotational energy. Another form of the motor is a linear motor, as you can see on the screen. It is used to convert electrical energy into linear motion. Just imagine if we cut along this line and press the conventional motor, will get something into this form. Linear machines resembles the principle and the topology of rotary machines by cutting and unrolling principle to obtain flat linear machines. So let's look at its working principle. When the primary of the linear machines gets excited by a balanced three-phase power supply, a flux starts traveling along the entire length of the primary. This linearly traveling magnetic field is equivalent to the rotating magnetic field in the stator of a three-phase motor or a synchronous motor. Electric current gets induced in the conductors of the secondary, as you can see here, due to the relative motion between the traveling flux and the conductors. Then the induced current interacts with the traveling flux wave to produce linear force or thrust. If the primary is fixed and the secondary is free to move, the force will pull the secondary in the direction of the force and will result in the required rectilinear motion. When we give supply to the system, the developed field will result in a linear traveling field. Just imagine a magnet placed on the rolling bar between the two magnets facing north and south pole. As we can see, if the magnet is placed in such a fashion that it north faces to north and the other side of the south pole faces to south of the another magnet, they will generate a repulsive force on this magnet and will push it to roll in a linear motion either forward or backward. Similar principle is used in the linear electric machines. Moving ahead, now let's look at its advantages and disadvantages. The first is linear electric machines have low initial cost and low maintenance. Unlike brushed motors, there is no contact between the moving parts in a direct drive system. Therefore, there is no mechanical wear, resulting in excellent reliability and a long lifetime. Fewer mechanical parts minimizes its maintenance and reduce the system cost. Next, we have no overheating, no limitations of maximum speed. Power to weight ratio is better than the conventional motor. In ironless linear motors, shapes is very thin and gives machines builder great flexibility in locating the motors. In addition, ironless motors provide no force ripple and have very low moving masses. Next, we have tractive effort does not depend on the speed. linear motors achieve very smooth velocity regulation with low ripple. Under disadvantages, linear electric machines have low power factor and its overall efficiency is poor compared to a conventional motor. Linear electric machines have been increasingly applied to different market sectors and proved their efficiency in various electromechanical systems. A linear motor is not that widespread compared to a conventional motor, however, but taking its economic aspects of usage into consideration, there are quite a few instances where linear machines is indeed necessary for some specialized operation. A few of such applications are listed here. First, automatic sliding doors in the electric trains, mechanical handling equipment such as the propulsion of a train or tubs along a certain route, metallic conveyor belts, or the pumping of liquid material handling in cranes, etc. Next, look at its design challenges. So, for a PMSM linear electric machine, we need a rare earth magnet, and as we know, the cost and the mounting instability increases with the stroke length. So this is one of the major challenges for a linear electric machines with permanent magnet assisted. Second, we have a large attractive force during operation which affects the system performance. Next, we need to minimize its losses and control the dissipated heat amount essentially when the load is mounted to the moving side which contains all the stator windings. Next, we have control of the moving mass and its effect on the thrust or the force which it generates. And the last, we need to analyze its dynamic stiffness and vibration when there is a periodic motion happening in the linear electric machine. So, to overcome these all challenges and to analyze the model, AMWorks provide a various electric machine solutions. First, we have the Motor Wizard tool. It is a template-based motor design software that allows user to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic, and transient solvers equipped with integrated analytical and finite element based solvers. Second, we have the AMWorks 2D tool. It is a 2D electromagnetic simulation software that uses the finite element to solve magnetic, electric, and transient problems. AMWorks 2D allows you to study the effect of the geometry or simulation parameters changes on the design. It also allows you to couple a transient magnetic study to mechanical motion and thermal. Third, we have the EMS tool. It enables user to do both electric and magnetic simulations using the complete 3D geometry. EMS is a true multi-physics software that enables users to couple the magnetic and electric design to circuit, motion, thermal, and structural analysis on the same model in a hassle-free integrated environment. So for our today's model, we will be using AMWorks 2D tool to design a flat type and tubular type linear electric machines. Next, before beginning the analysis, we need to set the model. So to begin the performance analysis in AMWorks 2D software, first, different study settings are needed to be done such as materials, boundary conditions, mesh, and windings. So let us quickly go through each setting and then we will discuss the performance of a linear electric machine. So once we open the material tab, we can assign different materials to the motor parts from the material database available in the software. Then we can set the boundary condition as air, then select the rotor part for torque and force calculation, and then finally set mesh control of the motor. Next, we have winding settings where the user can choose either current driven or voltage driven, and then set the amplitude and frequency of the supply, number of turns, and its diameter, and also select the direction of the current. After we are done with the setting, we run the analysis, and once it's completed, we can check the performance curve using the result tab. So to begin with, under case study 1, we'll be analyzing a single-sided flat linear electric motor as you can see in the animation. And here are the details. It's a 3-phase linear PM motor having a 8 number of poles with 12 slots. We are operating it at 50 Hz frequency with a mechanical speed of 0.6 meter per second and having a coil turn of 20 number of turns with an air gap of 1 millimeter. The overall motor length is 80 millimeter. And as you can see, we have since we are going to use EMWorks 2D software, we have simplified its 3D geometry into its 2D planar symmetry, as you can see at the bottom image. So to begin with, first let's go through its no-load analysis. So here we have a deterrent force, as you can see. It is caused by the attraction between the permanent magnet and the iron core without input current. So the slot effect is caused by the attraction between the PM and the slotting of the iron core. It has a wavelength of 1 slot pitch. The slot effects of deterrent force is analogous to the cogging torque or rotary PM motor, and for this analysis we get the deterrent force of around 135 Newton. And also another important plots are the flux density plot. Using this instantaneous flux plot, motor designer knows the behavior of the flux path and the region where it is saturating. Moving ahead, we have no load back EMF and also the magnet flux linkage. For this model we have obtained a back EMF voltage of around 7.5 volt, and also the flux linkage is good enough, which is around 0.085 Weber. Magnet flux linkage is nothing but the rate of magnetic field linking through a given conductor, and since it's at no loads, it's mainly due to the magnets mounted on the rotor core. And this waveform was also obtained at the base speed of the motor with no load or at no excitations. Next, we have obtained the thrust force. At the velocity of 0.06 meter per second, you can see we get a thrust force of around 1000 Newton, and which is in dynamic because the rotor keeps moving and there is always a attraction and repulsion force. Thrust is simply a static measurement of pushing or pulling power, and higher thrust does not necessarily mean the greater speed. And we can also see its on-load analysis, magnetic flux animation versus time. Next we have a current induced in the coils and also the voltage obtained using our EMWorks 2D software for a flat type linear motor. The voltage is around 13 volts and the current induced was around 120 amperes. Using our software you can also obtain the total winding losses, and you get a curve of the total loss, and you can see it's around 900 watt, and at the same time you can see the winding losses animations, which will help the designer to evaluate the total loss density, which will be responsible for generating heat. So it's very important to have this feature. Next, moving ahead, we are going to analyze a tubular linear PM electric generator. So the specifications are as follows. It is also a 3-phase tubular linear generator having a 4 poles and 6 slots. Similarly, we are going to operate this model also at 50 Hz, having a mechanical speed of 2.75 meter per second. It's higher compared to the previous model. We have used a number of coil turns as 76, and also we have designed this for 2 millimeter air gap. And this is a little longer model which has a stack length of around 350 millimeter. Also, we'll be using our EMWorks 2D software, therefore we have simplified our 3D model into its planar symmetry, and as you can see on the right hand side. So to begin with, we'll perform its no-load analysis into 2D software, and we get a deterrent force of around 200 Newton. And also similarly you can see its magnetic flux density plot, which helps a lot determining the flux path and how the rotor and the stator is behaving and where the part is saturating, and you can design your shape of your tooth and notches accordingly to avoid saturations. And improve the efficiency of your machine. Next, we again obtain its back EMF, flux linkage, and since, as we have seen, the air gap has been increased, therefore the overall coil flux linkage has reduced compared to the flat tire. But overall, anyway, we cannot compare both the motor together, and we get its back EMF around 100 volts. Since we would like to test this model in a generating mode, so it's important to connect a load across the three-phase winding. Therefore, we have connected a purely resistive load having a resistance of 0.04 ohms, and we have used this feature in our software along with transient magnetic study. You can couple the study using a circuit coupling to circuit. So simply just by activating this checkbox, you will get a circuit generator where you can use all the active elements to build your purely resistive circuit or RL circuit, or if you just want to go with inductive circuit, you can always use the type of circuit you want to connect, and you can do a lot of fault analysis using this circuit editor. So let's see its performance. These were the current which were induced due to this load connected across the generator, and we can see it's around 10 ampere, and also we can see its current density, how the rotor is moving and how the current is getting induced. Next, we also obtained its thrust force, and since it's operating as a generator, therefore we get a negative thrust force, and which is around 300 Newton, having a peak of around 750 Newton. Also at no load, you can again visualize its magnetic flux animation versus time. And for this model, we have obtained its total core loss, where you can see along with the total core loss, you can also obtain and segregate its component into hysteresis losses and the eddy current losses and also the excess losses. And by applying a simple average of these waveform, one can obtain the losses magnitude. Also, we have obtained its winding losses, which is copper losses generated in the model, and we see it's around 500 watt. Moving ahead, we have performed its thermal analysis. So we can see here that maximum temperature in the model is around 45 degrees Celsius, which is happening in the stator core, because that's where the heat is generated, or it's a source of heat generations, the current carrying coils. Therefore, using this thermal analysis, a user can understand how much heat dissipation is required from the motor, either by designing a better airflow path or incorporating circulating liquid jackets in the motor core. So that helps you to analyze so that you can control the heat generation and the temperature of your machine. Next, we also simulated our tubular motor design using our EMS software which is a 3D design simulation tool. And as you can see, you can set the velocity either in steps or either in like sinusoidal form, the way you want to set the linear velocity. So for this, I have set as a velocity in positive direction and negative direction, so that you can see a to and fro motion of your linear electric machines. And for this model in 3D, we obtained its back EMF. So as you can see, a very interesting curve, and as the rotor passes through a stator carrying coils, you see the back EMF is induced, and then once it's out, we get zero back EMF, and again when it's so between this to and fro motion, we get such kind of back EMF at no load. And also you can see it's a magnetic flux density plot, and as the rotor passes through the stator core, and you can see the flux circulating around the stator core. So let's move into the live demonstration of our one of the software, which is EMWorks 2D. So here we are into our SolidWorks platform, and EMWorks 2D is one of the EMWorks product. You can go and easily launch and open our software once you are into a SolidWorks platform. So I'll be demonstrating you the model where you have already sketched using the SolidWorks editor, and you have designed all the components of your linear motor which you need, or you have imported from the other software, or you can directly sketch, because we are into same platform and it's very hassle free. So once you've done with the model setting and sketching, such as it's a back iron, it's a magnet and different its windings and armatures, we click on the Invox 2D software, and here the next step is to set the material. So once you go into your material sections, as you can see here, we have set M19 grade electrical steel with having a 0.35mm lamination thickness for the stator armature, and also for back iron core. For magnet we have assigned N42 PM, and for winding we have chosen a copper material. Also we set a band and air region around the model. So once all these material settings has been done, we move on to the electromagnetic input setting, where we need to set its forces, load restraint and winding. So let's look at its forces. So these are basically the components we need to select, which will be responsible for torque calculation. So if you see here, we have used a torque calculation option and force calculation. So for a conventional motor we compute torque, but since it's a linear motor, we will be computing its force, and we select all the components which will be generating forces. So once we have done with the virtual work setting for the moving part, next step is to set the winding. So since it's a 3-phase motor, we need to have a 3-phase coils. So these are the coils for A phase, similarly for B phase, and also you can set the direction of your current, and you can see this is how it's very big. You can adjust its size so that you see a very small arrows, but yeah, these are the direction of the current, and this you can see for the reverse direction. So this is how you can set the direction, and you can confirm it once you're done. So once we are done with the winding settings for all the 3-phase A, B, C, next step is to set the mesh. So for the mesh, you can either use a mesh control to assign whether you need more fine or coarser size of mesh. So let's see the mesh for this model. Well, here we go. So these are the meshes for the slots, and for all the magnets and back iron you can set the mesh as per your requirement. And let's hide this mesh now. So next is the thermal input. So we will be having a conventional properties setting for the model. So we have selected all the edges of our model for a thermal setting, and the convection coefficient is around 10 watt per meter square Kelvin, and we have set the ambient temperature around 300 Kelvin. So this is how you set the convection properties. So once all the model setting has been done, you simply go and right click on the study and we run the analysis. Once analysis has been done, you can easily go into result section and click on result table to view all the plots. So to begin with, we get a lot of different results in this table, you can see. So let's look at its flux linkage. So once you click on the flux linkage, select all the 3-phase, or at a time you want to see just one phase, that's fine. You can click on this 3-phase, add into your parameter, and then you click on the plot preview. Here we have a flux linkage plot. Then let's see the voltage. We are going to add and plot preview. These are the voltage waveforms. If you are interested to look at its force, so we click on the force, and we have two force in X direction and Y direction. So since we are having a motion in the X direction, so we'll be looking at its Fx. So we add this into our parameter, and then we click on the plot preview. So here we see the force computed from this object. Next, let's look at its current induced. So here we have current induced. We add all the 3 phases into our parameter and plot preview. So these are the results which you can see in the result tables, and also you can look at its plots. So I click on the magnetic flux density, and then we click on show. So we'll have a magnetic flux path. Similarly, we can see the current density by click. So here we have a current density plot for all three phases. Also, you can simply right click on this model and click on the animate option so that it provides you animation versus time, as you have seen in our presentation. So it's very simple to use the software and to design the model whichever you need and get the electromagnetic, thermal and structural performance. So moving ahead. So well, in today's webinar, we have simulated two different linear motor topologies, mainly a flat type and tubular type using EMWorks 2D software, and we obtained its electromagnetic and thermal performance curves. And using this FEA tool, it helps the motor designer to have a better understanding of the motor operating it and its operating behavior under no load and on load conditions or fault conditions. It helps you to improve the overall efficiency. But however, in a nutshell, the selection of the topology, whether it's linear or rotary, is like a trade-off between the constraints, what kind of application you are working on. And at the end, we also saw the demonstration of the EMWorks 2D software and how to set up a model and design such type of motors. Here are the references. Thank everyone for attending the webinar today, and now the floor is open for a question and answer session. Thank you so much and see you in the next webinar. So to begin with the questions, first we have, how efficient are linear motors? Well, the efficiency for the linear motors are about 85 to 90%. Of course, it's lesser compared to what we have in the market. Rotary motors, especially the PM assisted ones. So now you might get a thought like there could be a workaround so that we can use a rotary motor and to convert them into linear motion by using some gear mechanism. So of course that is one option, but just to remember that in case like during the transmission of power from rotation to linear motion, again you'll have a wear and tear in your gear arrangement and your system will become bulky, and also there will be some losses. So it's better to use a linear motor where you need a linear motion, where your application is something with linear related to. So yes, so even though the linear motors are lesser efficient compared to rotary, but it's based on the application. Second, we have, is it possible to design linear motor without permanent magnets? Yes, of course. Like for our today's webinar, we have discussed a linear motor with PMSM like type, but of course you can have a linear induction motor where you need to use a series of conductors either made up of copper or aluminum. You can always simulate in the FEA tool, and as the traveling field will be passing through the conductor, it will generate it like mainly as like a induction motor principle. It will generate a current flow in the conductor, and you'll have a magnetic field to push this rotor into linear fashion. So you can have a linear induction motor, of course, without permanent magnet. Also, you can design a linear reluctance motor with the same principle for what we use for rotary motor. Next, we have, how do you determine the gap? So I think the gap, you mean air gap between the rotor and stator. So well, as an electromagnetic point of view, like from you want as minimum as gap between these stator and rotors to have a better like the fill to flow and to have a lesser reluctance, because air also provide a reluctance on your path. So for a better usage of this magnet flux and to have a good linkage with these conductors placed inside the stator core, the ideal case is to have as minimum as possible. But of course, these are like a practical, it's very difficult to achieve this tolerance. So generally we go with 0.05 millimeter air gap in the rotary motor. So, and based on the application and what kind of vibration you have, what kind of loading you're going to have, you need to have that margin such that you don't meet the static portion of your motor with the rotating, moving portion of your motor. So of course, air gap is obviously having a larger air gap is a loss. You are wasting your like lot of flux, and so it's not a very efficient motor. So we designed based on the manufacturing capabilities, the air gap generally, and also in what environment condition you have, and whether you have a dust environment or high temperature environment. So materials do expand and contracts under thermal operation. So you have to take care of all those features, because it should not be like once the machine is operating and your core get expand and then you start touching the other interference. There should not be any interference. So Many factors plays a role to decide this air gap between the rotor and the stator part. Next, we have what is the importance of back EMF? Well, back EMF voltage is the voltage in case of PMSM. If I talk about this particular application, it's generated due to the magnet flux linkage, which is like when I say, for example, when I say I have a 100-volt back EMF at base speed, so means that amount of voltage is induced inside this stator coils. Now, to drive this motor up to that base speed, you need to apply a voltage, which is nothing but a DC voltage or through AC voltage across. You need a voltage enough such that you are able to fulfill this voltage plus the losses in the into your conductors. So obviously the supply voltage should be higher than your back EMF voltage plus the losses inside the cables or whichever you have. Just in case, imagine if you exceed the supply voltage, your motor will be no longer a motor, it will act as a generator. So this voltage is very important, and based on your configuration, amount of magnet volume used, number of turns, this voltage is induced inside the conductor, and that voltage determines the speed to achieve to reach that amount of supply you should apply to reach that speed. So you can refer, and it's very common term. You can refer any textbook and go through it, so you'll have a better understanding of those back EMF term. So do visit our website. We have many interesting webinars coming up, and also if you have any suggestion, please contact us. And if you would like to see our any past webinars which you have already missed, you can always request for demand videos, and we'll be happy to share the webinar recordings with you. And yes, see you in the next webinar. Thank you so much.